My presentation is the journey of additive manufacturing at AGCO. Quick agenda, I'll introduce myself, introduce you guys to what AGCO is, what we do, and then I have a couple different areas of context. I'm going to talk about our adoption timeline, some of the phases of adoption that we've gone through and the time that it's taken to do those. Talk about some of my favorite applications that we've used at AGCO, and then conclusion, and we'll save some time for Q&A. I'm a manufacturing engineer at AGCO. I've been at AGCO for a little over 5 years now. I studied automotive engineering at Minnesota State Mankato and got hired shortly after graduating to come to Jackson, Minnesota and work at AGCO on the manufacturing side of the business. What is AGCO? So we're a global manufacturer of agriculture equipment, tractors, sprayers, combines, and everything else to do with agriculture. Some of our large brands that you maybe have heard of or might be familiar with would be Fendt, Massey Ferguson. We also have like Challenger, Valtra, Ideal, Gleaner combines. So the facility that I work at is in Jackson, Minnesota, and at that facility we build 6 different unique products. We build 2 different models of high horsepower agriculture tractors, and we build 3 different models of high performance agriculture sprayers. And then we also build a track suspension system for the Ideal combine. We have 900 employees at this campus. It's a 130-acre campus, and we're doing all kinds of different work. So we have a large fabrication shop where we're doing laser cutting of sheet metal, brake press bending, machining. We're one of the largest employers of welders in the state of Minnesota. We have second, third shift weld as well as fabrication. We also have robotic welding. And then painting, we do powder coat painting, liquid coat painting, we do inline assembly painting, and then we do full-blown assembly of our products. So from a rear axle that rolls in from the warehouse on a cart to a finished tractor that drives off the line under its own power. And we also have product design engineering, so there's over 100 mechanical engineers in Jackson that design most of the product that we build, as well as our product validation team, putting together the Frankenstein's builds for the next 5-10-year product, as well as the long-term field validation of the current products as well. So adopting 3D printing. Back in 2020, I'd like to say the phase that we were in was learning on a budget, and in 2021, we were able to take some of those lessons learned. We invested a little bit more in the technology with some desktop scale FDM machines, and then in 2023, we made an industrial grade deployment after we began to realize the true value of additive manufacturing, and brings us to today where we're trying to lay a foundation for the future and how we scale additive manufacturing. So it's okay to laugh at some of these pictures. This is the first phase for us back in 2020 where we're learning on a budget, and the only picture I could dig up of our old Lulzbot printer was one where there was a massive print failure. But yeah, in this phase in 2020, we had a lot of unknowns. There wasn't really any experts on site in terms of like, what is 3D printing? How can we use it in a useful manner? What are the materials? What would we even use it for? But eventually we started trying to find better applications for them. Like the part that you see in the bottom right corner is a TPU spacer that our assembly team uses when they're setting this, imagine a 30-foot long stainless steel air boom that weighs hundreds and hundreds of pounds, and they're setting it on our fertilizer system in the assembly process, and this prevents it from scratching up the boom rest, but also sets it at the correct space, and that's a part that's still on the production floor today. So we knew that, okay, there's something to this 3D printing thing, but with the equipment that we had, we knew that we were a little bit limited. So that brings us to 2021. We got a little project budget together where we said, okay, could we just spend a little bit of money to get some more modern printers so that we're a little bit more reliable, and we could also do some higher performance materials. And we started learning about some magical things like build plate adhesive and dryers for drying filament. This is really important if you're trying to print nylon composites or even TPU. These are hygroscopic materials that uptake moisture, and you're going to have a lot of problems printing with filament that has moisture in it. And at this point, we're starting to get better operationally, so we've started a methodology in how we save our work, and we're starting to deploy in applications all over the manufacturing facility, like paint masking, jigs and fixtures for assembly, quality parts. So I have a few examples of pictures from back in the day of some of our favorite applications back then. You can see a paint mask for a large machine surface. This is a really simple example. Basically, our engineering team, they'll outline, hey, this is where these 2 structural components mate together. We don't want painted surfaces mating together because in vibration, scenarios that paint could wear out, and that would adjust the bolt stretch on those torqued joints. So that's custom paint mask. Safety bumper on a weld fixture in our back shop. We have tons of giant weld fixtures, giant machine fixtures, and they all have sharp corners all over them. Handheld tools like this bulkhead adapter for an electrical bulkhead, and then a nylon carbon fiber adapter for some plumbing components that go on our fertilizer sprayers. So we were getting all kinds of different success stories that way. One of my favorite success stories was this large prototype project that we did. Our engineering team went to a machine shop, and this machine shop is responsible for producing the production tooling of these components. And in the past, they had just purchased bulk plastic and they'll machine the prototype components for our engineering team. Well, that quote came back to do all those components was around $120,000. And they came to me because they knew that I had 4 printers, and they were curious, hey, how long would it take to print all these components? And I said, well, it's going to be a couple months of printing, but we should be able to get it done. So we ended up doing it in nylon carbon fiber for around $3,000 in material cost. So engineering looked at that and they're like, wow, this is fantastic, because we got our 5 proto units built, they're out in the field accumulating hours, and we were able to avoid that really non-necessary prototype cost. The value lies in solving problems that you can't normally solve or you don't even think to solve. Huge umbrella term, and we're going to look at some more applications, but solving problems for continuous improvement in the manufacturing area, and then cost-effective rapid prototyping is huge applications. So at this point, we're a year and a half into our more robust deployment of additive manufacturing, and the question comes, what's next for us? At this point, we have a need for more durable parts. With the layer boundary weaknesses that you get with FDM printers, you can't always make completely drop-proof parts. And when you're giving a welder a tool to go use in the back shop, you can guarantee it's going to get dropped, it's going to get thrown, it's going to get beat up. You need something that's a lot more durable. We also had a need for more geometric complexity and a need for more capacity. So at this point, we started doing some more research in other industrial 3D printing technologies. This is one slide from a research phase where I created single slides for our leadership team that explained, hey, this is this industrial technology, here's how we could use it, and here's the potential ROI if we were to invest in this technology and how we would use it. This is the slide for powder bed fusion. Basically, we had a scorecard in the bottom right. Powder bed fusion polymers scored pretty well for us. So that's what we decided we wanted to invest in next. So then the next phase was to benchmark the industry leaders. So we went out to all the industry leaders in the polymer powder bed fusion space. We gave them some conceptual parts that you can see on the right and said, how much would it cost to produce this on your machine with your materials? What would you recommend for print orientations and that sort of thing? And after evaluating all the different companies, we ended up deciding to go with HP's multi-jet fusion solution. So here's our equipment that we invested in, we installed in 2023. So we have a HP multi-jet fusion printer, AMT blasting cabinets, AMT vapor smooth, and dimension coloring. And part of the reason why we went the full gambit and not just the printer is because we knew in our evaluation phase that a piece of the puzzle that we needed to get into was end-use parts. We build tractors and sprayers, and we build them at pretty low volumes. So every year we build 700 tractors and we build 1,000 sprayers. And those products are highly, highly configurable. So it's very common that you'll have a component that's one per not even one tractor. So we have a lot of examples, and I'll show some in the future slides. We found a back corner in one of our assembly halls and taped off an area about 2,000 square feet, and then this is kind of the finished result. You can see I wheeled over the old Raise 3D printers because of course we were going to continue to operate those for various other materials. That brings us to today, where we're operating this equipment and we're trying to do different things in the business to lay a foundation to scale additive manufacturing. We've implemented more into our business system, so we've created manufacturing work centers in our SAP business system, so that way we can actually issue off material, route parts, and we're calculating and adding labor times to all the components that we're manufacturing, just like we would for a sheet metal part that's going to go get cut on the laser, bent on the brake press, welded, painted, all that. And then we have things like our SharePoint site, which you can see in the top right, where engineers and shop floor employees can go to this website and they can enter a ticket where they can request something to be printed. So if I'm an engineer and I have a prototype that I want to just get printed for fit up, I can come here, I can enter my ticket, add a part file and it'll get printed. And if I'm a shop floor employee with an idea for a continuous improvement, you can add that as a ticket, explain the problem, and that'll be our backlog essentially for us to pull from to go and evaluate and do our tool design work. We're implementing TPM calendars for equipment maintenance, very, very important. So that way we're staying on top of maintenance and minimizing failures. We're also doing workshops to help educate and train employees in Jackson. So we invited over, I think it was like 70 or 80 of our mechanical engineers to come to the 3D print area, and they could look at example parts, and we went through a brief presentation to show them, hey, this is what you can do, this is what you shouldn't do, and here's how you get started. We did the same thing for all the shop floor employees as well. Even though they can't provide us with the design file, it's good for them to be aware, so that way when they're working in their areas, they can come up with these different continuous improvement ideas. This month marks 18 months since installing our multi-jet fusion printer. We've done almost 12,000 parts. Next, I'm just going to talk about some of my top picks for applications. So the example on the left, this is a jig for holding a digital protractor that snaps onto the nozzle of our sprayer. So here is a 120-foot boom section, and on a 120-foot boom unit, you have 400 nozzles. It used to be a two-man job. Somebody hold the protractor and the other person adjust the plumbing, and I'll tell you when it's zeroed out. Well, now you can put your protractor in there, snap it to the nozzle, and one person can do this job. Reduces the time, improves the quality. Go, no-go gauges for checking for non-conforming parts. This is a structural casting in our hitch assembly on one of our tractors, and what this gauge is checking is the spline geometry. So we were receiving parts from the supplier where this casting would fit up, and we would go through our assembly process, and that might take it 2 or 3 hours of work content, and then they would go to start moving the hitch, and they would find it's out of alignment or the cylinder is bottoming out. And so what was happening is this spline geometry on this rocker arm was clocked incorrectly. And our quality team was having a heck of a time trying to figure out, how do I inspect all these and validate what's a good part, what's a bad part. We ended up MJF printing this tool that drops in, and basically you can see on the left, if it drops in, the part's good. If the tool doesn't drop in, it's bad. So we were able to make a bunch of different versions of this tool. We sent all of those to the supplier, and we said, check your own stuff. Stop sending us crap. And we have, of course, some copies in-house, and we just double check when we're doing our assembly process. And then another jig on the right here. This is a radar row guidance that mounts on the side of our sprayer, and the angle at which it's pointed at the ground is critical for its calibration, and that's just a factor of how these bolts are tightened on these brackets. So this is just a little jig you just put in there, and it bottoms out at 45 degrees, tighten up your bolts, you get your angle right every time. Another application is paint masking. On the left, what you can see, these are MJF printed and vapor smoothed molds, and then on the right you have the resulting silicone cast part, which is the actual paint mask. The advantage of doing this is we can use an industrial grade silicone, which is temperature resistant all the way up to like 800 degrees Fahrenheit, so it can go through our powder coat ovens as well as our liquid coat ovens. We can embed magnets, which is these little dimples that you see on some of these parts, and it's exactly the correct shape for the machine surface, the bore, or whatever it is that we don't want paint. So we've done a few different examples of replacement parts. Pretty simple one on the left. This is a hanger that's on the gun of the powder coat gun. For some reason, this bracket costs like $100, and they break like every 2 weeks. So we ended up taking a couple of the spares, we 3D scanned them in our quality lab, and we just 3D print our own replacements now. They still break every now and then, but the maintenance guys told me that these last longer. We had an instance where the maintenance team was trying to repair a power floor jack that we use on the assembly floor, and this tank was leaking, and the floor jack is old enough you can't source this tank anymore. So they just gave me the leaky tank. I redesigned my own version of the tank, MJF printed, vapor smooth it so it's mostly sealed, and bolted it back on the floor jack, and we're up and running. And then all the way on the right, that's a special tool called a Huck bolt gun, and basically it installs a special fastener, and it does so with hydraulic power, and we were having an issue where these custom hydraulic lines that go into the gun, the operator has to get in all these weird little spaces, so they're putting a lot of stress on those hydraulic lines, and we were breaking hydraulic lines almost like every other week, and they're long lead time, expensive hydraulic lines, so we just made a simple strain relief that goes inside the pistol grip of the gun and helps those hydraulic lines reduce strain and last longer. Prototype parts. This is kind of a fun slide to make because apparently it's frowned upon to show prototype parts. So all these parts are either failed concepts or they're actually in production now. You can see on the left a hydraulic cylinder cover. Sometimes things change on the cylinder, we add a new center, whatever it is. Now that cover has to change. We MJF printed this and we were able to do the review with marketing. So we printed those, fitted them up, and validated that. Vents for an HVAC system. This was an idea to change the vent location in the cab inside of our sprayer. With this little adapter, they were able to take the existing dashboard and just plug these in, and that would simulate, oh, if the vents were in slightly different positions all over the cab, how does that feel to the operator? And then all the way on the right, may not look like it in the picture, but that is a very, very large part. That's a manifold for vacuum on a prototype planter. The outer diameter of this part is 380 millimeters, which if you're familiar with MJF is a pretty special number because that's the maximum width of parts that you can fit in the printer. And actually, Master Graphics printed this part for us because this was about the time where we were waiting for our equipment to be installed. Without this part, it was a long lead time part. The validation team was unable to put the planter in the field and start accruing hours on all the other systems on the planter that need to be validated. And then end-use parts. So we have a few different end-use parts right now, hoping to grow that in the next year or so. Simple examples here, like a reflector bracket. This is a homologation item for our tractors. This reflector is on the side of the unit. We designed the bracket to hold the reflector and it looks fairly aesthetic. This is an adapter for a vent to one of our fluid tanks. So on top you have your NPT threads and an air filter which allows atmospheric air to flow through down to the fuel tank as the level gets lower. And this replaced actually a small assembly and reduced the labor time pretty significantly. It's about 400 parts a year. And then we have this bracket here for supporting the dipstick tube. On large equipment like tractors, your dipsticks are very long, and so the tube can be really flimsy, which can be kind of tricky when you're trying to get everything lined up and put back in. So this replaced a stainless steel bracket that was a pretty tricky 4-bend stainless steel bracket. So now it's just a much simpler, more elegant solution to support a dipstick. In conclusion, there's still a lot of opportunity for us. We're still learning, we're still growing, and we still have a lot to improve on in our additive manufacturing journey. My key lessons, I would say, is that learning takes a lot of time and effort, and it's important to have a resource dedicated to that. Sometimes you hear stories of companies that have tried 3D printing and they just think that you can just buy the equipment and magic things will just happen and you'll save all kinds of money, and that's not really how it works. So you're gonna have to dedicate a resource to, hey, we got this new piece of equipment. It's just like any other piece of equipment. There's nuances to it. And it's important to dedicate that resource to learn those nuances. Another thing is don't be afraid to experiment. In your experimentation, there's going to be times where you're going to succeed and there's going to be times where you're going to fail. But sometimes the failures, you'll learn something that you didn't think you were going to learn that might be useful in other applications. And then one really fun thing in the last few years as we've been getting better at this in AGCO Jackson is engaging the workforce and improving culture with 3D printing, especially in terms of lean manufacturing and continuous improvement. So we're at a point now where I walk down the assembly hall and someone waves at me, I got an idea, and they're thinking about it in terms of the work that they do all day, every day, making it easier, safer, higher quality, more cost effective. And that's been something that's been really exciting and cool to see as we've rolled out 3D printing in Jackson. Go ahead and start cheap, start small. The value that you find on a small scale will scale proportionately as long as you support it with the correct resources and time and effort. So if you can prove something quick and dirty, cheap and fast, you can probably expect to see similar return on an industrial level. I just wanted to say thanks for DI Labs for all the awesome education things that you guys do. I think it's a fantastic thing in the additive manufacturing space, and thanks for having me here. And any questions?